Hello, everyone, and welcome to today's webinar, Learn Your Total Cost of Ownership with the Menardi TCO Calculator. I have just a couple of notes before I turn it over to Dave. We have set aside time for questions after the presentation, so please type any questions you have into the box on the left labeled Q&A, and we will answer them as many as we can during the session. If any of you have any problems with audio, video, or other technical issues or questions, please comment them in the Q&A section of the webinar screen, or you can email me at christina.quick@menardifilters.com. You can make the webinar screen full size by clicking the four little arrows in the upper right of your screen too. And now we will begin today's webinar, and I want to introduce to you today Dave Thompson. Dave is Menardi's technical director. He has over 39 years of experience in all aspects of the solid liquid separation, with in-depth exposure in production and production management, sales and sales administration, engineering and product development, application engineering, and general management. He is truly an expert in both dry and liquid filtration. So Dave, now I'm going to turn it over to you.
Great, Christy. Thanks so much. Welcome, everybody. As Christy mentioned, we're going to talk about the baghouse operation and what we call the total cost of ownership. At Menardi, we come across on a daily basis customers that frequently have questions about why don't my bags last as long as they could, or can we make them last longer? Can we make them perform better? Can we continue to meet the requirements as put out by the EPA and being enforced right now? So we get into that with this total cost of ownership. What we try to do is help our customers walk through not only just the bag issue they may be having, but all of the other ancillary equipment and functions that go along with the baghouse, so that we can truly understand where the source of our problem may be, and how to correct that. But we do that by looking at the entire baghouse. So I'm going to go back to what our main sheet here, and what we have on our main sheet. We use this to help us select the proper filter bag for an application, one that will help you to will give you the most life for your particular application, and then we add into that all the other operations that go along with that. So you've got your whether it's a pulse jet, a reverse air, or a shaker baghouse. Obviously, each one has its own special cleaning needs and so forth. So we go into each one. Typically, we run across pulse jet. We do quite a bit in reverse air, but we do run across pulse jet. This particular exercise will be with pulse jet filters. So we try to give our customers the best advice we can based upon all the different factors of their particular operating system. So when we look at a baghouse, we talk about the Dust Collection Operation Balancing Act, and that's what it is. So everything centers around making that dust collector work right. For energy efficiency, production, environmental compliance, and reliability, and cost of management and maintenance. We try to provide the best. So we know that if our customers are using the best available technology for preventive maintenance, for process control, and the best filter media technology, they've got a real good chance of helping to make their system as effective and as efficient as possible. We always know that there are process limitations, and these are things that we take into effect, such as the age of the equipment being used, the design parameters. We look at air to cloth ratio, the interstitial velocity, the type of cleaning system, whether it's on demand or on time, inlet configurations, and so forth. And then we look at process conditions, of course, the gas stream, the temperature involved, grain loading, moisture, and bulk density of the solids. We boil all that down to a strategy where we feel that if you choose the right partners who are offering support beyond just a bag, you're going to get a system that's going to work better. So we offer at Menardi a long-term corporate commitment to our customers. We're a 100-plus-year-old company. We've been involved especially in compliance with the EPA since the Clean Air Act back in the 70s. We have put together a support structure of salespeople, internal staff, technical, and upper management that is focused on bringing about the best possible solution to our customers' problems. We focus on continuing education so that we always know what's out there relative to the different types of filter media and operating systems and so forth. And then we focus on compliance and system efficiency. We've had quite a few customers this year come to us because the EPA has asked them about the types of bags they're using, their compliance, and can they get better, or are they in compliance, and how can they stay there? So we take all these different variables. Obviously, in this case, this is a pulse jet application. We look at the inlet airflow. Now, in all three scenarios, that's going to be the same. What we do know at Menardi, quite frequently we get to a customer and baghouses are undersized, or they're pushing a lot more volume through than it was originally designed for, which is not uncommon, very, very common. Typically, there is a safety factor built in when there's a design, so they can increase typically without adversely affecting the system's operation. But by stressing a system, you always put more stress on the bags. You can wear them out sooner. You can stress the equipment in ways that you normally wouldn't have, especially if it's related to temperature and so forth. So we like to know what the system is actually, what the actual flow rate is in the system. So we use that. In this case, we would use that same flow rate for all three scenarios. And what we're trying to do, this is a customer who has standard polyester bags right now, standard polyester felt bags. And we look at that and say they want to know what they can do to make their system better, make their bags last longer. Typically, and this is spoken like a true bag manufacturer, we get to a customer, it's typically not the bags that are the problem. It's everything else that goes around the bags and helps them work. So we try to address those things because the bag is what it is. If it's an inexpensive polyester bag that's been selected, there are certain things you have to do to make that bag work properly. And typically we'll make a suggestion on how to make that happen. We'll also suggest possibly a different type of bag that can get the customer the kind of performance they're looking for at an overall price that makes their system more cost effective. So when we start to look at those things, in this comparison, we're comparing polyester felt bags with a standard, with our Menardi polyester felt bag with a low drag membrane, which is for us is fairly new technology. And then our standard option two would be our standard polyester felt bag with our standard Microtex expanded PTFE membrane. It's an older technology; it goes back 30 years. So what we do is we look at the bags. There are certain things that don't change within the system, whether it's a standard felt bag or a bag with membrane or not. The bag size, the overall length, and the quantity of bags in a baghouse. Typically, that's standard. It is what it is, no matter what type of bag you use. So we like to calculate. We always calculate the amount of filter area in a baghouse. This helps us to determine our air to cloth ratio. Critical in a bag system. If we don't have enough filter area to handle the incoming airflow, then of course we're going to have problems with differential pressure. We're going to have problems with fan efficiencies, and we're going to have problems with compressed air use. So we look at those things. We put all three. We put the data in to calculate air to cloth ratio. And on this particular sheet, it's going to be the same no matter what type of bag, because it's the same number of bags that are the same size bags, independent of the type of bag that it is. So we use as a rule of thumb, air to cloth ratio for shaker bags is 1.5 to 1 and up to 3 to 1 for a shaker bag, air to cloth ratio. Reverse air, it's 1.5 to 1 to 2.5 to 1. And in the pulse jet, it's 4 to 1 to 7 to 1 air to cloth ratio. In this particular case, we're a little under. We're at 3.29. We take all of our bags and we take the total area. We're at 3.29 to 1 air to cloth ratio. That's good. That should keep your differential pressure low. It gives you enough area to handle the volume of flow coming through the baghouse. And based upon that, it's sized okay. It's good. Other things to consider in this, and we'll talk about that further on, is grain loading or dirt loading, and the type of particulate that you're catching. That can affect that, even if your air to cloth ratio is good. So the next thing we look at is fan efficiencies. Now in a standard operating system, um, standard bags, a standard polyester felt bag will typically need a Precoat on it to help it work properly. It's got to be Precoat's got to be introduced to the bag, because as a standard polyester felt bags, or any kind of standard bag, whether it's polyester, aramid, polypropylene, um, or Riton, they all have an air permeability between 25 and 45 CFM out of the box. So in order to make that more efficient, typically a Precoat is used. That Precoat reduces the air permeability, protects the surface of the material from dirt being embedded in it, and makes the bag last longer. But there's a cost for that. And what happens is you can't run your differential pressures as high with those, because you have the ability, you can force media or dirt into the deep matrix of the media, and then blind the media off prematurely, and so it fails. And then you'll also be constantly replacing Precoat. So we look at that first scenario with the polyester bag, and we see the system flow is what it is. The current differential is 6 inches of water column, and they're using 218 horsepower to run that fan and to make it work properly. So based upon those calculations, we know that with a standard bag, it's going to cost you almost $180,000 a year to run that fan on a standard operating system. And our option two, our low drag material, because it has a membrane on it, and that membrane is very unique in that it has a higher differential pressure to begin with. However, it flattens out and stays flat for a long time. It allows for longer time intervals between pulsing, therefore making the bags last longer. And then the last scenario is our old type of PTFE membrane. Lower differential pressure to start than the low drag. However, it does increase as time goes on. So you end up with a higher differential pressure. You can run them higher because typically the membrane protects the substrate so that you don't have to worry about embedding material. So in each one of those scenarios, with the same type of system, you're using less horsepower, and therefore it's costing you less money. Now, on the low drag, you go from 180,000 on a regular bag to 120,000 with low drag. That's a big difference. And that's something that can be put right in your pocket and goes to the bottom line of your plant operating costs. And we just talk about how we calculate the horsepower and the total efficiencies and stuff of that system. What you have to look at and keep in mind with standard bags is that standard bags typically wear out from the inside, because in a pulse jet system, you are putting this bag on a cage. We recommend and specify a certain pinch or a gap around the annulus of the cage, between the cage and the bag, so that we don't prematurely wear the bag out. However, if you're pulsing too often, or if your pulse cycles are not what they should be, short, robust bursts of energy going through to clean the bags, if they're longer and less effective, you can begin to wear the bags out from the inside. And that's typically what happens with standard felt bags. What we're trying to do always when we look at someone's system is say, how can we get you away from pulsing too frequently? And one, in our eyes, that's always pulsing on demand rather than on time. And the other is to only pulse at the proper differential pressure. This way, we're not wasting energy, we're not over pulsing and wearing the bags out prematurely, and we're giving the system its best chance to operate as efficiently as possible. So we calculate the use of compressed air with each of the different types of bags. Now, typically, a standard felt bag with a Precoat on it will have to pulse more frequently. You cannot run a differential pressure higher, so that drives you to pulsing more frequently on demand. And the reason we recommend on demand is because you don't have this unnecessary motion that you're going through with this baghouse. Systems that pulse on time quite frequently pulse too frequently and will pulse off all of the Precoat that you've seasoned on the bag and got it to work effectively, and now you've pushed it all off. So you've got to reintroduce that and get your baghouse back in good operating compliance. With membranes, we don't worry about that as much, and we're not here just to drive membranes on people. What we're here to do is get the most efficient system for a particular customer based upon their operation and their application. But we have found over time, and with the cost of membranes having come down, that membrane bags can be quite cost effective. And even though there's a slightly higher upfront cost for them, they're much more forgiving, and they allow you to operate right from the start without having to worry about seasoning your bags and making sure they're working properly. So when you turn the switch on a system with a membrane bag, it's ready to run. Um, because we can run them at higher differential pressures, there's more time in between pulse cycles and cleaning cycles. So that is a cost savings right away. Um, um, Typically, membrane bags will have a longer life because you're not wearing them out and you're not pulsing as much. So there is a benefit to having a membrane bag, both in ease of startup and then length of life and durability. So we make this comparison, and we still have lots of customers that like to look at these bags and say, "Oh my gosh, I can spend $15 or $20 for a standard polyester bag, and in the end, I'm gonna it's my upfront cost is not going to be as much, but in the end, it does cost them more money only because of their use of energy and their use of compressed air and so forth. Compressed air is expensive to create and to produce, so we want to try to minimize that. Um, so when you look at these different scenarios, we talk about using all the same type of cleaning system for all of them. But when you change the pulse time between the time between cleaning cycles, you pulse less. Therefore, you consume less air and less energy. In the low drag bags, which tend to get to their differential pressure and flatten out, you'll find that they're the least expensive to pulse. They may cost $15 more per bag, $20 more per bag, but in the end, when you're pulsing much less and less frequently and using less energy to do it, you are creating a good situation. Now, standard membrane bags, they still have a little higher differential pressure. They still have you can increase the time between pulses, no doubt about it. However, because the differential pressure on that bag begins to creep, it does cost you a little more to you may reach terminal differential pressure faster, and you may pulse a little more. Again, you don't run the risk with a membrane bag of pulsing off the precoat, which is really important. We'll get into how we look at precoat and so forth as we go forward here. So this is another important part. You've got your air to cloth ratio, you've got your pulse cycle and your cleaning cycles that you need to look at. And if they're in line, then you will have a system that'll operate fairly efficiently. If they're not, if they're out of line, if your air to cloth ratio is way off and you don't have enough filter area to accommodate the amount of flow rate, you're going to have a problem and you're going to pulse more frequently. So another real important area to look at is interstitial velocity, and we calculate it for two different ways here. We calculate it for round baghouses and we calculate it for rectangular baghouses. Um, and what that interstitial velocity is the measure of the upward airflow going through the baghouse. So remember, in a pulse jet system, the system's online all the time. You take off rows at a time and pulse them, and then there's an irregular pattern for doing that, so that you don't pulse dirty bags next to clean bags that you just pulsed. One of the key factors in this type of housing is the interstitial velocity, and that is, can the dirt that's on the bags that's being pulsed off, does it have the ability to fall off and actually drop into the hopper and be evacuated from the system? Frequently, we find that because the upward airflow is so high in some of these systems, and you may have a light powder, it doesn't get a chance to evacuate itself. So frequently, you will pulse a lot more, because what happens is, because the dirt can't get off the bag once pulsed, it becomes re-entrained on those bags. So that does two things. It shortens your cycle. It creates a higher differential pressure, and it causes three things, and it causes you to back pulse more frequently. So what we're trying to do is optimize that that interstitial velocity, and it kind of is what it is. A baghouse, when they're set up, and you've got the number of bags in it, and basically what we call the ligament on the tube sheet, that's the dead space on the tube sheet that doesn't have a hole in it. that is the free area that allows dirt to fall off. If that's really, really close and you've got bags that are bridging, it may be difficult to get that to happen. But there's ways you can change that, you know. However, it's a crucial part of the system, and people will say, "Boy, I post all the time, and you know, my runtime between cycle, my runtime between cleaning cycles is getting very short." Well, typically it's because they're re-entraining that dirt back on the bags; it's not leaving. Um, Membrane bags tend to pulse better, but the real function of that interstitial velocity really is that space between that ligament between the bags or that area between the bags, and then the um, bulk density of the material that you're trying to push off, and how much of it you're trying to push off. Those things all play. So grain loading, bulk density or weight of the material, and the area between the bags is what's crucial to making a bag house clean properly. Typically, when they're sized properly. You know, they're sized properly so that you have an interstitial velocity, and our rule of thumb in an interstitial velocity is somewhere 300 feet per minute or less. If your upright airflow is higher than that 300 feet per minute and you've got a light material, it's going to be tough to pulse off. We try to keep that in mind. What can happen in situations where you may have a more dirt load than you thought you were going to have? You may have to pull some bags out to get the stuff to fall off, to create more distance between those bags. However, what that does do is it cuts down on your air to cloth ratio, so it can make your filtration a little less efficient. There's a compromise there. It's a tough thing to remedy once you've got this problem. So key to know is the bulk density of material, and can it fall off and be evacuated. If it can be, and the system's operating cleanly, then it's going to be much more efficient. Again, overpulsing uses a lot more power and a lot more air to get these things to clean properly. And in the end, they may not clean right at all. So, as I said, we calculate interstitial velocity based upon round bag houses and square bag and rectangular or square bag houses. So there's two different uh, calculations here: round, and then this is rectangular. Um, so we try to make that as efficient as possible. Down here, we give you a little data, some rules of thumb, basically for where the bulk density of the material may fall, and what that maximum upward airflow could be to help so that this material falls off efficiently. If not, if you don't fall into these realms, you're going to have, or these ranges, you're going to have a problem with trying to get the bag house clean. 90% of the bag houses that we go to where there's a problem and the bags are not cleaning properly or not lasting long, it's typically because they cannot evacuate the system properly. We find this a lot, especially in long bag technology, in bags that are 20 feet long and plus, or 30 feet long, 25 to 30 feet long or more. Typically, they do not evacuate as good as they should. Typically, the bags will sit in ash or will sit in particulate hot material at the bottom of the bag house and can't get out. That shortens the life of your bag. It reduces the amount of area you have for filtration, and it creates a real problem. So it's important that you try to adhere to these ranges. You know, so particle size is critical. Agglomerating or non-agglomerating material, critical. Inlet loading, critical. Moisture in the system, critical. You know, so all of these things are areas that you need to look at, pay attention to, and will help. We can help you remedy a situation possibly by changing the evacuation system, the hopper, the screw conveyor, whatever it is that's taking the material away. Key to know, it's important to know, especially when they design the system, as to what the actual evacuation system is. Unfortunately, folks, most of us have inherited the bag houses that we have. So you've got to make them work. We're just trying to help you take a system that is inherited and may not be running too good, and help you to work better. Talked about before in the beginning, pre-coating. And when we calculate pre-coat, um, hold on, sorry, calculating pre-coat and leak check. So we calculate them the same way, basically. For pre-coat, this tells us how much many pounds of material we need for to pre-coat a bag properly and to season it properly, so that on a regular felt bag you can get the proper pre-coat, so you get the right filtration. There's a cost associated with that, and then there's a we show the cost per pound or 30-pound bag of the material. This can be quite expensive over time, and so it's another reason that we don't push, but we like to recommend in cases where we can membrane bags, because typically you don't need a pre-coat to make the bags operate efficiently. They operate efficiently right out of the box because of the membrane that's been laminated to the surface of the felt. When we look at leak check as well, and I know I called the leak check here. We look at leak check. When a bag system when a baghouse change is made, the system is then once it's completely installed, the system is then checked for leaks to make sure that we have no leaks at the tube sheet, that we have no bags with no bottoms in them, or if we've got some compromises in our long seams or whatever it may be, we run a leak check. An iridescent powder that with a blue light, we can see places where leaks may occur in a brand newly installed baghouse, and we can correct them before we fire the system up and foul the whole baghouse. Leak check is important. Most people use it nowadays. Some people don't, but it's really critical. It helps us to help you make your system run better. Remember, if you've got a baghouse with 250 bags in it and you've got 2 bags leaking, you may not think that's a big deal, but those 2 bags foul the entire baghouse upon startup, and it makes the entire baghouse less efficient. It won't work as well. Once you backblind the bags, you now have a problem where you've got dirt on the clean side of the housing, and it's going to cause problems throughout the entire time that those bags are installed. So it's critical that we run a leak check. We calculate leak check and we put it into our equation at the that we talked about for the total cost of ownership at the very beginning. One thing to look at, I can touch on this real quick here, and this is the difference between regular bags and membrane bags, and why one is different than the other, and why one works better than the other. This just gives you an idea. And I wrote here, the issue of air permeability and increased airflow with a membrane versus standard felt bag is a little fuzzy. The term lower average differential pressure is what is key. If you've got a lower differential pressure with a standard or with a membrane bag, typically it's easier to operate than it is a bag with Precoat. So although the air permeability of a membrane bag is slightly lower initially than a properly seasoned felt bag, the media will perform at a higher level of consistency and efficiency. Regular bags that are pre-coated and seasoned properly over time will have issues. And these are the issues we get into because you're talking about a depth filter. That's why there's an issue. And what we show you here is that here's an unpre-coated bag, and here's a standard bag with no pre-coat and a standard bag with pre-coat. The pre-coat is protecting the bag, the substrate, from the particulate. Here you have no protection. You have no pre-coat. Pre-coat's critical. Once this dirt gets into the matrix of the substrate, the bag is fouled and it will be for life. You won't get it clean. The same thing can happen here in a pre-coated bag. However, it takes longer for that to happen. This pre-coat protects it. It blocks it. High differential pressure will push some in there, but typically it can stay on the bag. It can be you can pulse off your dirt and then start your system up again, no problem, without having to reintroduce more. If you're pre-coating and if you're back pulsing on a regular basis, this will last for quite a while. However, you can get dirt entrained. The membrane filter is a surface filter, and these photographs you'll see under high magnification what membrane looks like. The cross section of membrane, although it's like a couple thousand thick, this is what the cross section looks like. It's a very complex matrix of the membrane itself. That membrane is being put onto the surface of a felt material, which is a really good carrier because it has a very high open area and creates a situation where the bags will clean efficiently for quite a long time without pre-coat, without worry that they're going to become blinded, or you're going to force dirt through. Of course, you always, as I said, leak check these systems, whether it's a standard bag or a PTFE bag. So another consideration in baghouse and making bags last is temperature. You know, typically we have customers come to us and say, gee, we're having excursions, we're having temperature problems, and we're getting an excursion on a polyester bag. We're looking at a bag that operates somewhere around 275, 280 efficiently. And they'll say, well, we have excursions up to 325, up to 350. Well, what's the excursion? Well, sometimes they last minutes, sometimes they last 10 minutes, and then the temperature will go. Well, an excursion like that, in any case, no matter what kind of bag, if you're stressing the bag by putting too much temperature on it, you are making the bag weaker over its life. Temperature has an ill effect on bags in that you lose dimensional stability. So once dimensional stability goes away, the memory of the bag goes away. So when it pulses, it doesn't come back into shape properly. It's important to make sure that you use a bag suited for relative to temperature for the application. If you've got a bag that's on the edge, then you're probably better off going up to the next bag, even though it may cost you a little more. In the end, it will last longer and it'll operate longer. It'll operate more efficiently. It's really important. So this is a good guide. This is just a general frame of reference for you to look at bags, and then it also gives you some other areas where the bags may or may not operate well, and it's something to consider depending on your process conditions. So when we go back to our total sheet here and our total cost of ownership, and we start looking at this, we look at it and say, okay, so if we've got a standard bag, we know that those bags, total cost of those bags is only $57,000 for a regular felt bag. That's pretty inexpensive. Low drag bag would be 128, and a less expensive Microtex bag, old type membrane, is 100,000. When you look at that and you look at the amount of energy used to run the fan in that type of a system, and the amount of energy used to produce clean compressed air for cleaning and so forth, the costs start to change. And so we also look at what type of system is it? Is it a negative system or a positive system? Are you pushing dirt through or are you pulling it through? We need to know, just so we know that, on what type of system it is. So if there's problems, we can go back and look at that type of fan for that type of application. Again, typically a tough thing to change on a system, but it's good to know. Cage cost kind of is what it is. So we're going to say the cages are, for lack of a better, just for this example, that they all cost the same. So we're looking at cages that cost us $57,000, and in addition to what the bag cost is. When you look down and you throw all the things into what we talk about, when we look at the cost of running a baghouse, we talk about what does it cost to have a bag change. What does a planned shutdown cost? And these are your numbers, are just for reference, but given this that they're the same across the board, and we're doing that just to show you that there is a savings in the end, in one way over the other. With standard bags, you've got to use a Precoat. There's a cost for that. There with all the bags, there's the use of leak check, which we include in all of them. There's the cost of labor and the time to perform that leak check. It's the same for all of them. But in the end, when we look at the type of fan, the horsepower consumed by the fan, and that the fan produces, and the cost of it, and then the cost of compressed air for cleaning bags, the changes begin to become quite evident, and the differences become quite evident. Here, all of our air to cost ratio is the same for all of them, and in the end, without any fancy stuff on the system like broke bag sensors and particle monitoring systems and so forth and controls, you're looking at a savings for the most expensive bag in the overall life of running that baghouse of $13,000 a year, which goes directly to your bottom line. Now, if you've got other things that you can do in your system to control the system better, to put the proper controls on your system, you may even be able to squeeze more efficiency out of your system. What we're trying to show you here is that it's not always necessarily the least expensive bag that's going to get you where you want to be and save you money. In the end, typically that's not the case. So we try to make the case for ease of operation, and making sure that your system is reliable right from the start. So if you go to the EPA, and the EPA has published a document that accepts that goes into all different types of bag filter media that's used, but what they like to hang their hat on nowadays is using a membrane, so that you get the capture efficiency that you're looking for and the life that you're looking they don't really care what it costs you to run the system. They just care that the system's going to do what it's supposed to do relative to what's being put out into the atmosphere. So so um, so in the end, um, we're looking at systems that can operate more efficiently depending on the type of filter media and the cost of the bag. Even a more expensive bag can can um, can be very, very effective for a customer in the end. We have made changes for people, and we work every day with all different types of filter bags. But we lately have made changes over to these different types of membranes in several cases in the cement industry, in the steel industry, and others, to make systems more efficient and more effective. So that's our goal here at Menardi, is to help our customers become experts with their own baghouse and to help them gain the most they can out of that system. You've got to have these systems, so you might as well take advantage of making them work properly and efficiently to save you money. We all know that in most places, these things are a cost drain. So if we can make that drain less, it's a good thing. In process systems, this can really help a customer improve their process and make their process more profitable. So with that, are there any questions?
Thank you, Dave. And we do have a few questions, and if anybody else has a question, just use the chat box on the Q&A side on the left-hand side of your screen, and we will get to them. Our first question, Dave, is from Daniel. We currently do not have this data. How important is it for us to find it?
So I'm assuming that's the process data. So it's real important. Any of our salespeople can tell you, we go into plants all the time, and we start this process of crawling into what the problem may be. And we say, okay, so what's your actual flow rate? And they say, well, I'm not really sure. It varies. It's between X and Y, but I'm not really sure what it consistently runs at, or what's your operating temperature, what's your grain loading. And frequently they don't have it. Now they can get it, and they do, but knowing this kind of information is really, really important. Not only to you as the person that's running that plant or is in charge of that or responsible for it, but to anybody else that comes in that wants to help you make it work better. So you go back to your original design data. Obviously, plants like Dutch baghouses, large baghouses, get built over years. It's designed in year one, and it's actually put into place and fabricated and put into place in year three. Their operating conditions may have changed, or their demands from the plant may have changed. So you look at what's the design parameters, or original design criteria, and then you look at what the actual is. We're real concerned about the actual. So that information is available. Now with process control being what it is, and on a different scale now, it's gotten better everywhere. Usually it's available. So you go back to your control room, you talk to your process engineers, and they'll fill you in on what it is that the system, how the system's operating.
Okay, thanks, Dave. So another question from Sean is, how do you remedy a situation where your upward airflow is higher than it should be?
Well, as I mentioned, there's not that much you can do about that. And typically what some people do is, if their airflow if they can compromise between losing a little bit of filter area and pulling some bags out and giving them more area between the bags, so that the material has more of a chance to drop off. That's what you do. So we offer things like tube sheet plugs, so you can pull bags out and you can plug holes in tube sheets. We don't recommend you pulling out that many bags because it's very difficult, but sometimes it doesn't take that much to alleviate. I shouldn't say alleviate the problem, but you can make the problem less of an issue. But if you had to remove some bags, that's probably one of the only ways. And again, you're compromising by taking away filter area, shortening bags, and so forth. That doesn't do a whole lot for you, because this is really based upon the area that the bag takes up, and it's that hole that's in the tube sheet that the bag fills that's really calculated. It's the bag bottom that you're calculating versus the entire tube sheet and all the number and the whole number of bags that you've got. So you can do things to help remedy. If you can cut back on dirt load, if you can reduce your grain loading, then that can help as well. So you could do the combination of removing some bags, reducing grain load, and all of a sudden you may have a situation where you can evacuate the dirt properly. Remember, if you can't evacuate the dirt, then the bag system is doing you nothing. If you can't properly evacuate what falls off the bags and send it to where it's supposed to be sent and get it out of the system, then the bag system's not working for you at all.
Okay, Dave, looks like we have one more question, and it's from James. Can you give us an example where this TCO has been effective?
Yeah, we've gone to several customers and talked about this and got them to um, uh, look at what we're talking about and they've made some changes, and we've been in the cement industry and some finish mills and things like that where they've gone to a membrane bag and or they've gone to a low drag bag in the steel industry. That has helped them. Now, what they typically will do, customers will do, is they'll start out. They may change out a couple of compartments with material one compartment. We've done it even in the we're running tests right now up in the petrochemical industry. We've had some successes in a couple, three different industries on and shown that this type of approach can make a system work more efficiently, can help you to stay within EPA standards for particle discharge and smokestack issues, and increase overall efficiency in the baghouse and make it less expensive to run. So again, in cement and steel and petrochemical, we've had some good successes.
Okay, thanks, Dave. And
Yeah.
thank you, everybody, for your time today. And as a reminder, we will be sending out a recording of this webinar shortly. And if your question wasn't answered, a Menardi representative will be in touch with you within 24 hours. At the end of this webinar, there will be some poll questions. Please take the time to fill those out. The feedback helps us tremendously for future webinars. And as always, you can visit our website for more information at menardi.filters.com. And we thank you and we look forward to working with you in the future.